Good afternoon. We're just waiting a minute or two more till everybody enters. Okay. Good afternoon, or depending where you are or when you're watching, good morning and good evening. Welcome to our webinar series hosted by the Euro-Mediterranean Center on Climate Change, known to most simply as CMCC. I'm Jeremy Powell, a senior researcher at CMCC. I'm in the Risk Assessment and Adaptation Strategies Division, or RAS, which is located in Venice, and it's also part of our Institute for Climate Resilience. Before we begin, I'd like to take a couple of minutes to promote CMCC. This is our 20th year. We're celebrating our 20th anniversary as a leading research center focused on understanding the interaction between climate change and society. We're based throughout much of Italy, but our network is global, as shown with our partner organizations that are located worldwide. As far as our mission goes, we're sort of a one-stop shop from models to solutions. We advance climate research through multidisciplinary analysis. We combine climate modeling, impact assessments, and environmental economics, and we support science-driven adaptation and mitigation actions. Our research infrastructure is designed to support our transversal and multidisciplinary competencies that combine climate modeling, impact modeling, and environmental economics. Our divisions are distributed across 3 multidisciplinary research institutes. We have 4 strategic programs on frontier topics. We have state-of-the-art high-performance computing facilities, and we have 2 specialized centers on digital innovation and high-level education and training. I'll describe all of these in our next slides. Our research institutes are the Institute for Earth System Predictions, which is focused on climate modeling, the Institute for Climate Resilience, focused on representing the key components of the Earth system, and lastly, the European Institute on Economics and the Environment, which is focused on the intersection between the environment, technology, and the economy. CMCC also has 4 recently developed strategic programs. The first is the integration of the planetary biogeochemical and industrial carbon cycle to support the transition to a low-emission economy. The second is predicting socioeconomic impacts of climate change to support adaptation within policy and investment frameworks. We have the Global Coast as the new frontier to develop digital twins of coastal phenomena, and integrating AI, or artificial intelligence and machine learning in the modeling chain to enhance modeling and large-scale data analyses. In addition to the 4 scientific programs, CMCC has 3 centers. Our high-performance computing center, which is the most powerful in Europe and in Italy, and one of Europe's most advanced. We have an advanced digital innovation center and an advanced training and education center. So with that brief introduction of CMCC, I now have the pleasure to introduce Angelo Campanale. Angelo is a postdoctoral researcher in CMCC's Regional Models and Geohydrological Impacts Division, which is also known as REMI, which, like the RAS division, the Risk Assessment and Adaptation Strategies Division, is part of the CMCC's Institute for Climate Resilience. Prior to joining CMCC, Angelo was a postdoctoral researcher in the Department of Mechanical Engineering and Management at the Polytechnic University of Bari, where he also earned his PhD, I think, a few years ago. There, he focused on numerical and experimental characterization of cartilage tribology, with an emphasis on the lubricated contact between viscoelastic surfaces. In CMCC's REMI division, he's now taking this knowledge of fluid dynamics to work on integrating urban parameterizations within regional atmospheric models to investigate urban atmosphere interactions. In fact, today's presentation is specifically on that work, which will also include key insights and challenges and applications. Before I pass things over to Angelo, if you have any questions, comments, suggestions, anything you'd like to communicate to Angelo, please do so in the Q&A box at the bottom of your screen in the Zoom Q&A box. And hopefully, if we have time, we'll get to them at the end of the presentation. Angelo, thank you for joining us today. The floor is yours.
Thank you, Jeremy, for a nice introduction. I'll share my screen for the presentation. Okay. So thank you, Jeremy. So today I will talk about some insights and challenges and also application in regional urban climate modeling. And in particular, the outline of this webinar is the following. So motivation and goals. So why the urban parameterization are really important in regional climate models and how these are taken into account in climate models. Then I will focus in detail on the results of our recent study, but basically we developed, implemented urban parameterization in the next third generation model, atmospheric model ICON that previously was a well-established urban parameterization in the Cosmo model. And I'll show you some application over and interesting results over different cities. And then I'll focus on some further developments. So how can we still improve our urban models, and what could be and what are the challenges in the urban climate, and finally some conclusion and final comments. So I would like to start with this question. So why do we need an accurate urban representation in regional climate models? So and I would like to start with this quote from the third working group of the sixth IPCC assessment report. So basically, despite occupying a very short part of the land, urban areas are one of the most incredibly important sources of greenhouse gases emissions, and of course can have a big impact in climate change scenarios. And indeed, one other important thing is that urban climate research has also been traditional unrepresented in the last IPCC report. For example, in the 50 IPCC assessment report, there was no inclusion in cities. And of course, we are focused in our division on regional climate models, and when you push with resolution, when you have high resolution climate models, of course, if you neglect the presence, the effect of the cities, you can have big bias in your model. For example, here I show you the urban representation of Bologna during an heat wave of last July 2023 in the ERA5 analysis dataset. That is basically one of the state-of-art dataset for climate representation at global levels. And as you can see here, there is no signal from Bologna, while it is well registered in the observation at high resolution. So of course, if you push with the resolution, you need to have a better physical representation of cities, and of course also the cities start to play a role from a morphological point of view, because you have high resolution to characterize all the processes. And still, also, I would like to emphasize the fact that the relevance of our study, the importance to have a correct representation of the cities in urban climate models is not only an important pillar of the PCC, or here I quote another goals of the United States but also it is completely aligned with one of the goal of the CMC of our institutes. Indeed, here at the bottom of the slide, I quote one of the sentence in the Institute for Climate Resilience homepage where we are saying that basically we plan to investigate climate change from regional to local, including urban and variability in the extreme events. And one of the solution could be, of course, one of the solution could be, of course, proper parameterization of the urban process. So if you plan to provide correct adaptation strategy, you have to physically being able to proper parameterize this process, because of course at regional scale the cities start to play a crucial role. And what are the possible application of having a urban representation in climate models? There are tons of applications. There are tons of climate change related problems that can be tackled. Of course, cities have impact. Of course, the first thing is impact on population, it's stress, mortality, but also energy cycle, water cycle, greenhouse gases. We're talking about heat island, the fact that urban environments start to create a strong temperature anomaly if compared to the rural surrounding, air pollution, and so on. So it is nice that now, for example, we work on a specific urban parameterization, but in general, when you have a urbanized regional climate models, you can tackle a lot of climate change problems that without a proper representation of the cities is basically impossible. So now I would like to focus on how the cities are represented in climate models. Of course, there are different level of sophisticacy, different level on complexity. So the main driver is, of course, the horizontal resolution. So if you push with the resolution, you have enough resolution to start to see urban canyon, urban canopy, and to see how these interact with the land, with the atmosphere. And here I put a basic classification. Basically, we have in global models the so-called zero level of urban models. So basically, there is just a reduction in vegetation. Of course, if you are at very coarse resolution, you are interested more in the climate phenomena in a broader area. But when you go to mesoscale, we're talking about from 10 kilometer, even to 1 kilometer, even to the so-called convection permitting scales. There are too many different too main possibility to model the presence of the city. Basically, there are the so-called bulk models that use bulk formulas. Usually the canopy is squeezed basically, or just a single layer. These models are very fast. And for example, the one I show you, that is called TerraUrbet, are very easy to implement, but they are very accurate, and at mesoscale resolution, they provide very nice, interesting insight in the impact of cities on the regional climate. Then there are the urban canopy resolving models. These are not full resolving model, but they start to resolve some three-dimensional processes in the urban canopy. And these are usually multi-layer, but the problem of this model that start to became computationally demanding. So there's most of these models problem to run longer climate simulation, and also to they required a lot of input parameter that most of the time are not available in the common land cover datasets. So they are provided just in very local datasets specific to some cities, and of course, if we want to study global satellite cities, this could be a problem. And then there is this when we still push with the resolution, we are very, very finer scale. We're talking about hectometric scales, so ranging from 10 to even 5 meters. And here the process start to be very fully resolved. You can have models with indoor energy balance. They are able also to provide natural-based solutions. So you can change the morphology of the cities. You can increase the number of green element, for example, and you can see what is the impact due to the presence of more trees or more parks, for example. But there is a big bottleneck of these models that are very too much expensive, so they cannot run at all at climate time scale, but they can run just some days of forecast basically. And I think that as a sort of nice compromise and between computational demanding and also sophistication, we decide to go for bulk models that is called TerraOrb, and I will show you in the next slides. That was previously implemented in Cosmo, and now we have been also ported into the Icon model. So what is TerraOrb? So the urban canopy parameterization I will talk about you today. So it is basically offers an accurate description of the urban physics and its interaction with the atmosphere through bulk formulas. So basically, these are the three processes, the three physical processes that are taken into account. So you have thermophysical properties, basically when you have cities, when you have buildings, concrete that are in your model, they have an increased thermal capacity and heat conductivity, and they are able to store energy, to retain energy, and then to slowly release them, and to slowly release it. And this is taken into account through analytical formulas. Radiation properties. So basically, when you have a canopy, you have a sort of trapping effect of the solar radiation, and indeed also this contribute to have a decrease basically of the albedo, and also turbulence properties. Of course, you are putting an obstacle to the wind, to the vertical wind distribution, and all of these processes are taken into account in TerraOrb through very simple formulas that are also easily to implement in a climate model. The model is also online coupled, not only with was online coupled with the Cosmo that is an atmospheric, that is state-of-art atmospheric models, but also with a land use model that is called Terra. The same land use model is also used in Icon, and is coupled with this multi-layer soil model to take account for surface energy balance and soil water budget. The model is it is based on the so-called style approach. So basically, if you want to have a better representation of urban cover heterogeneity, you have the model is able to divide the pixel into sub-pixels. So to take into account of rural element, artificial element, from example, element coming from town representation due to town representation, and also water bodies. And this, of course, can have a big benefit in, especially into represent the different heterogeneity of a city. And it takes also into account the anthropogenic heat flux emissions. So of course, you have anthropogenic activities on in cities, and also the model is able to take into account of this external heat term, basically. And in the icon representation, in the icon implementation, now there are also new functionalities. Basically, there is also the possibility to somehow tune the urban cover, creating a nice gradient from the center of the city to the periphery. And this was a new function that was not implemented in Cosmo. This is very nice because basically you can start to tune your the model on your selected case study areas. And there's also the possibility to have an annual cycle of anthropogenic heat flux. That, of course, it is more realistic because I have a anthropogenic heat flux with a sort of seasonality can have a big benefit, can have a big impact surface energy balance, basically, while before there was a constant term to take into account of anthropogenic heat flux. And so I would like, so Terra proved to be very robust and efficient. And in our recent article, we investigate its ability to represent urban Thailand over the two biggest Italian city, Rome and Milan. And also now it became operational in, for example, at the German weather services in different configuration. So, but Terraorb, why we decided to implement Terraorb in Icon, that it can be considered as the successor of the Cosmo model, because Terraorb in Cosmo was implemented with a very successful historical track. So basically here I show you some examples, some literature example, where Terraorb was used to characterize some key meteorological feature of different cities. In Wouters et al. Was used over some Belgian cities. In Vertsev et al. 2020 was used on the Moscow big metropolitan area. In Brous et al. 2018 was used in a study to correlate urban heat Thailand and malaria disease over Kampala. And in Uganda, in Adonolf et al. 2023 was used to improve the urban representation if compared, for example, with ERA5 for Rome and Milan. And here, for example, I show you a study we are working on currently that this is a urban Italian of Athens compared with the Cherari analysis, so a gridded observational product that basically, as you can see here, there is almost a perfect matchup with observation also in this case study area. So in front of this successful history, Terraorb had to be implemented also in Icon. And indeed also due to the fact that all the community, here I'm representing the CLM community and also the Cosmo Consortium that were using Cosmo Consortium for weather timescale, the CLM community for climate timescale, decided to migrate to move to the new model, the Icon, that is basically this flexible, scalable, and high performance infrastructure for both weather and climate applications. And it is one of the next next generation Earth system model, and now the community is very big near Icon. That's why there was this project that is called PP Città project, priority project Città, that stands for Heat-Induced Temperature Change Through Advanced Modeling, led by Jan-Peter Schulz. It is also one of my colleagues that work with in our division at CMCC, but also at German Weather Services, to implement basically the urban parameterization Terraorb in Icon. Now the implementation has been accomplished, and I'll show you some results of our work. So in our recent work, basically, we decided to, once the implementation in the Icon code was completed, to assess its ability to capture urban heat Thailand over Rome and Milan. And we select this, the summer 2017 as period that was particularly prone to urban heat Thailand formation. Indeed, there was the so-called heat wave Lucifer in the southern Europe. And for example, in Italy, if we look at climate of the past over Italy, it was the third hottest summer in the Italian history. So it was a very interesting period to assess the new urban parameterization in Icon. And to prove the validity of our implementation, we compared our results with Cosmo model, because of course the same parameterization was previously implemented in Cosmo. Now it's been implemented in Icon, and we want to see how much different are the two models, and with the same urban representation, and also with observations. So this is basically the setup of our simulation, so of our experiment. We decided to focus on Milan and Rome. This is the domain that we used at convection permitted scale. So we're talking about simulation at approximately 2 kilometers of resolution. we used in blue. I here highlighted the domain of both models of the simulation, and in red the boundary, the forcing, the domain of the boundary condition provided by IFS SMWF model. And the case study area are basically Rome and Milan. In particular, the experiments is interesting because we use the same urban parameterization and also the same urban fraction. The urban fraction in the Terrell parameterization is based on the impervious surface area that or ISA. That is basically the key parameter for TerraUrb, is the most crucial one, urban canopy parameter, because it basically provides you the percentage of urban cover that is representing the cities, and for here to assess the comparison between Cosmo and Icon, and to make the model as comparable as possible, we decided to use the ISA based on the same ISA for both simulation. And here are some details of our simulation. In particular, we select the entire August 2017 as analysis period, with the entire July as a spin-up period for both models. So same urban parameterization, same land model, same land cover dataset, similar resolution, 2.5 kilometer against 2.2 kilometer, with TerraOrb activated and deactivated. And so here we looked at the spatial distribution of urban-rural anomaly during daytime and nighttime. So here we have Rome, here we have Milan, at the top Icon, at the bottom Cosmos simulation, and we are comparing the urban fraction that I showed you before for Rome and Milan against the temperature difference of the simulations with TerraOrb activated minus the simulation with TerraOrb deactivated. So we are looking at temperature anomaly over cities during daytime, during nighttime, and during daytime over the entire August 2017. As you can see here, clearly, the first conclusion is that without TerraOrb, you cannot capture these temperature differences, and so you cannot capture the urban-rural anomaly that I'll show you later is completely also captured by observations. And this, of course, could lead to a strong cold temperature bias, or even we're talking about 3 or 4 degree of bias, that's quite huge. And the one interesting thing is the fact that the results in terms of magnitude of differences are comparable, but are not the same, because are slightly strong in Cosmo, as you can see here for both cities, and while in Icon, the difference are a little bit smoother, so a little bit lower in the magnitude, let's say. Basically, this was due to the fact that in the Icon simulation before, meaning in the Icon model, the TerraOrb deactivated simulation take also into account of a parameter that is basically a sort of zero level of TerraOrb, when basically you are taking into account the presence of the cities, but just for the hydrogeological cycle. So basically you are paving your pixel, and no water can infiltrate, and no water in the moisture can evaporate, but just for hydrological cycle, not the other processes I showed you before on TerraOrb were activated, while this parameter was not taken into account in the Cosmo with the TerraOrb deactivated. So that's why the differences in Icon are less pronounced. And similar also in the vertical. So the cities can also have impact on the planetary boundary layer. And we also want to see how the model can, how the cities can have an impact on vertical levels of the models. And here I show you still temperature difference between the models. So TerraOrb activated minus TerraOrb deactivated for both model or the 2 different cities. In particular, I show you the meridional mean and the zonal mean and its correlation with the ESA, so basically the information of the urban cover. And the other important thing here is that basically the temperature difference are strongly correlated with the ESA distribution. So the peak are very perfectly positioned where the peak of temperature are perfectly positioned where the peak of the urban cover are placed. And still here, we want to have a sort of benchmark between ICON and Cosmo. In Cosmo, the urban parameterization was well established, and still here we are able to reach similar, of course, not same results because there is still a intermodal variability, but comparable results, and meaning that the implementation was successful. And finally, we looked at urban on subdaily dynamics, in particular focusing on a comparison with observation for urbanite island and the diurnal cycle, in particular here for high dense networks of station provided by the regional environmental agencies for both Rome and Milan. I'm plotting here the urban signals for both cities, the rural signals, and their difference, that is basically the so-called urbanite island, so the difference in temperature between the urban environment minus the rural, the surrounding rural one. And as you can see here, the important conclusion is that basically with no urban representation, so we are talking about the dashed lines, so with the in both model without TerraUrb, there is no urbanite island. I mean, slightly one, but it is a very with a very low magnitudo, and this could, of course, lead. I mean, we're talking about 2 or even 3 degrees of bias that are very, very huge, and while the performance of both models are very good in representing both urbanite island and also urban diurnal cycles. And also another important another important thing that can still confirm that the implementation was correct, that basically the rural cycle, when the parameterization is activated or not activated, is that, I mean, the signal remains the same, so there is no big impact, but just the urban representation is enhanced. And of course, if you want to have more details and more technicalities on the analysis we conducted, I can refer you to our recent article. So now we basically assessed the goodness of the implementation of TerraUrb ICON, and now we have the tool. Now we started to apply it in the different case study area. For example, here we have the Paris case study area. So in the Codex community, there is the flagship pilot study called Urban RCC, that stands for Urban Regional Climate Change, that aims to understand the impact of urban areas on regional climate. In the first stage of the simulation, the idea is to simulate coordinate simulations to analyze 2 short extreme events that hit the Paris region in the 2020, and of course in the future stage of the project, also urbanized climate scenarios will be provided. The simulation strategy is the following. So basically we start from era 5 reanalysis, so we're talking about INCAS simulation, then downscaling them at 12 kilometers over the Eurocordex domain, and then to go to at convection permitted scale, where cities and urban processes start to appear. And okay, and no, sorry. Oh, I mean, the CP stand for convection permitting domain, as I suppose was the question by Jeremy. And because we are talking about a 3 kilometer domain where cities start to become relevant. And the idea is to focus on 2 short extreme events and then to go for longer climate simulation in the next stage of the project. And here we analyzed 2 short extreme events, one heat wave in August 2020 and one convective event in May 2020. So, and these were the first results of the Codex ensemble. So basically here I'm showing you the urban Thailand, so still temperature urban signals minus temperature rural signals of the stations over Paris represented here. So red ones are the urban station, blue triangle are the rural ones. And as you can see, we were very, very satisfied with these new results. Basically, icon, the blue curve was one of the best performing simulation in the Codex ensemble. And even better that a lot of other regional climate models of the Codex community were even more sophisticated urban representation, urban parameterization were implemented in. And we, SMCC, participated with also Cosmos simulations and as CLM community, there is also the Karlsruhe Institute of Technology that participate with Cosmo. But I mean, the results were quite good with the TerraOrb. I want just to mention here the yellow line by Cosmo. This bias of 1 degree was due to the fact that actually and this basically the simulation based on EcoClimap second generation dataset was very good in urban representation. I'll show you later this the use of this dataset based on local climate zones, but was let's say very bad in rural representation. That's why you are killing your urban Thailand, because of course you need to have a good urban representation, but also good rural representation that is not depend on the urban parameterization, but most of the time is depending on the model itself. And a similar conclusion we can also say for the relative humidity. We are here I'm plotting the so-called urban dry island that is basically the same concept of the urban Thailand. So you have urban environment that is drier than the surrounding rural one. And as you can see here, still icon with the newly coupled with TerraOrb is still the best performing model in the if compared to some members of the Codex ensemble. And this still on Paris, another application, but a different time scale. So here there is the research demonstration project over Paris 2024, coordinated by Valérie Masson, that is one of the most important urban climatologists in the world. Is the developer of the thermal energy balance. It is also another interesting urban parameterization. And different meteorological services participate. Of course, also, for example, the German Meteorological Service with ICON, including TerraOrb in its simulation. The mesh size is very high, so we're talking about hectometric scale at 500 meters of resolution. And the idea was to provide accurate forecast at hectometric grid for the Paris 2024 Olympics. And here still I'm showing the results during an heat wave with the DWD that represent icon plus TerraOrb compared with the other urbanized with other forecast with other urbanized model. For example, also we have ICMWF that in the last operational cycle activate also an urban representation, and still icon with TerraOrb is basically the best performing one in the at simulate this extreme heat event. So I'll show you that basically when you go to convection permitting scale, so 2 or 3 kilometer, even higher icon with TerraOrb is very good. It's able to in first results I show you is very good in capture some of the key predominant feature of cities. But what could be the further development? What how the model can still be improved? How can we reach better representation of cities? And in this regard, the so-called local climate zones frameworks framework can give an help. In particular, the local climate zones were introduced by a seminal paper by Stewart and Oak in 2012 and are a sort of classification for urban and rural landscape based on different thermal, geometric, and surface properties of these two environments. And the idea is to have a more heterogeneous environment for the cities. For example, the results I show you, the urban land cover of created for ICON was based on just one urban class. So you basically have your land cover dataset, and you have a point that can belong or not to an urban class. That is, I mean, it is a very poor representation. And now we can improve this with local climate zones because in this framework are provided the 10 classes. So you can have here, because of course not all the urban points are the same, so you can have here a very urbanized environment with tall buildings, for example. But if you in LCZ1, but if you go to LCZ4, you have basically an urban environment with sparse building, but also the presence of scattered trees, plants, and so on. And of course, when you are providing the urban fraction to your model, you need to take into account also this urban diversity. And indeed here, for example, we start to work on this in the Cosmo model. This is one of an interesting work of my colleague Carmela. Indeed, in a predictal 2023 was shown that basically with the ecoclimate second generation, an impervious surface area, an urban fraction based on this dataset could improve the results of TerraUrb. And this dataset was implemented in Cosmo model, and that's why the next plan is to also implement this dataset into ICON. And here I can I'll show you, for example, some preliminary experiment still on Paris for the FPS tour project I've showed before. And as you can see here, the curve with the ecoclimate second generation, if compared with the station that are just in the center of Paris, or with different that can clearly represent the heterogeneity of the center cities, are improved with the presence of a ecoclimate second generation based on local climate zone dataset. And finally, I would like to also put some stress on challenges. So one of the challenges when you start to study urban climate models is that to a proper evaluation of your model, you need high quality observation, both in space and also time. And often conventional station data are not freely available, are missing, are sparsely, so they are not too much dense to represent all the urban environment, or have very low resolution in time, for example, daily. And this is, of course, it is a big problem. And in this regard, the so-called CWS data, the crowdsourced data, that stands for citizen weather stations, can provide a nice solution. So basically, these stations are networks of public sensors that are used by pedestrians or anonymous people from their home. And has been shown that this network of station can provide a nice solution. And the difference between these networks of stations, because you're talking about very compact sensor that can be used, are not so much they are not so much different in the performance of these stations if compared to the classical meteorological stations. And indeed, in this work of Berlin, it's very interesting to see that the difference between the CWS crowdsourced data and the classical meteorological station is very, very low. And of course, these start to be interesting from urban climate modeling studies. And another, I want to mention also the Carmine project, because in this project we plan to use this the CWS network station for example, for the case study area of Bologna. In this project, this is a project focused on urban climate modeling on different 8 case study areas. And we is in the work package 2 is focused on urban climate activities. Of course, it is a very big European project, and but in work package 2, the idea is to provide high quality, high resolution quality data for different case study area. And we are focused, for example, on the case study area of Bologna that wants to address the problem of heat waves for elderly people, for example. And the idea is to use ICON coupled with TerraUrb to simulate at very, very high resolution the past climate and future projection of the cities. And we plan to use this sort of new network data to validate our model. And another important application that could, help us to the lack of high quality observation, for example, is of course satellite data. This is a work of my colleague, Davide Morelli, that is a CMCC PhD student. And he's working on, for example, urbanized Thailand calculated from land surface temperature data of satellite data. And here you have the fact that you can have a very high resolution in both space and time. And this, for example, was a work he developed for the community of Sassari, for example. And as you can see here, there is clearly also an interesting effect due to the increase of the magnitude of urbanic Thailand during the year starting from 2014 2023. And of course, these are these two solutions are just not you cannot focus just on one solution, but you should have a sort of cooperation between all of these 3 solutions. So classical weather station, weather station, yes, satellite data and cross-source data to overcome this problem. And finally, we can come to conclusions and final remarks. So basically, to address the impact of climate change on cities and vice versa, urban parameterization are crucial. So if you push with resolution, you will have 2 big bias if you neglect urban parameterization in your model. The bulk urban parameterization TerraUrb is both accurate, efficiency is very fast. There's no impact on computational efficiency of the model. It was very well established in Cosmo. Now it's been implemented in its successor, the ICON model, and the ICON model has already been proved to be able to capture some key urban meteorological features. The model can still be improved. For example, enhancement in land cover datasets, such as the dataset based on local climate zones, for example, can further improve the representation of the heterogeneity of urban environment. And of course, if you have a nice urban parameterization, the model is good, but if you do not have an accurate, high quality data, observation data to evaluate your model, this is a problem. And for example, and not always the classical stations are available. And in this regard, crowdsourced data and satellite data can offer valuable alternatives. So this led me to the end of the webinar. So the results presented here are highly promising. But of course, this is just the beginning. Now that we have this new tool, that we have the urbanized ICON model, it is just beginning. Now we are poised to address a wide range of climate change related to cities. And that's the end of my presentation. Thank you for your attention.
Thank you, Angelo, for your presentation. We have just under 10 minutes for questions and a question and answer session. Many of you have already posed questions, but please do pose your questions in the and comments in the question and answer box. Angelo, I'll start off with an easier one for you. it says, how can citizens and NGOs access tools and data? So I guess someone would actually like to run the model, and they I guess they're interested in how available it is.
I mean, how cities can have access to, I mean, how citizens can have access to climate, to the model output, basically.
Well, I think they might even want to be interested in running the model itself.
Oh, okay. So actually, Icon now is open source. So also with TerraOrb parameterization. So of course, it is just matter to have access to the code to, of course, compile it and have the computational power to run the model. But everything is open source, also with urban parameterization, and also there is documentation to activate all the parameters in the nameless switch to run the model and to start to analyze your case study areas. But everything everything is there with, of course, also the urban parameterization in it.
Okay, maybe you can post a link in the chat. And I think the same person was interested in accessing your slides, so maybe you can make those available as well. There's a question here that just came in about how the computational time changes with your parameterization. How, what percentage increase did it add to the simulations?
Actually, TerraOrb has a very low impact. We did not. I mean, I do not have mm, details about it, but there was a common paper basically to assess the impact of TerraOrb in Cosmo, for example, Trusilov et al. I think 2017 or 16, and they basically investigate the impact on the computational efforts of TerraOrb, but is basically less than 3% for Cosmo, and similar, I think, is also for Icon. So basically, when you run the TerraOrb activated or deactivated from the computational point of view, there's I can say no impact. So yeah, the parameterization is very fast.
Okay. There's a question here about do you have an example of cities in more complex terrain areas and how the complex orography, I guess, of the area impacts your parameterization?
This could be a very interesting topic to address, but I know that there are, for example, some of our Swiss colleagues that start to address the impact of TerraOrb in Cosmo for some Swiss cities in the Alpine Valley, and still the model had good performances. But yeah, it is myself personally, I did not still study some case study areas in complex orography, but there are some work in the literature with that are using TerraOrb as urban parameterization to address this interesting problem. And I mean, it is also something that I would like also to start to study now. But yeah, there is some example in the literature, and that have been used to address some nice faunal or other interesting phenomena in the cities with complex orography.
Okay. You showed a lot of examples using temperature, the urban heat effects on temperature, but I could see this modeling framework to be important for human health considerations such as like heat stress, hospitalizations, and even fatalities. And as you know, humidity is also a very key driver of heat waves. And you did show a slide on relative humidity, but I'm wondering if you've considered some of these interactions on your parameterization with humidity and how that impacts heat waves. It also brings, I think, a question in the chat as well. I was wondering that I think was asking about air quality and if you were able to use your your parameterization for air quality. So the question is basically on heat waves, including the humidity effects, and then also about air quality.
Yeah, this is a very interesting question. So there is, first of all, we now that we are studying the problem of the heat stress over Paris, for example, in the Codex community, and we start working on a new manuscript basically to assess the heat stress over Paris in the simulation, the results I showed you, and we are of course starting to watch it. For example, of course, specific humidity and some heat stress indicator, and to see how urbanized model are able to provide some insight on this. And I mainly at the moment I mainly focused on relative humidity, just for the fact that also for Paris I focused on relative humidity and not a specific one. Also to mention this because most of the time when you need to evaluate your model, there are no measurement for specific humidity, but just on relative humidity. And relative humidity, of course, is more temperature driven, but is not a proper representation of the not the proper driver of the moisture in the atmosphere. So that's why I focused on relative and not on specific humidity. But just because most of the sensor that most of the station that you use to evaluate your model provide the relative and not specific. But yeah, there are still working on to see to see the impact of both temperature and humidity. And also regarding the air quality, I would like to mention that Icon has also a module that is Icon Art that can be run also with TerraUrb, that take also into account the coupling with the atmosphere, with the aerosol that are calculated by the model and not prescribed one. That, of course, this is a very interesting topic, and also to address, and there is the possibility to run at very local scale Icon Art with the TerraOrb implemented it. And I think it is something that it is a problem, the air pollution at city scale, that can be addressed in the Icon modeling framework. Yeah.
Okay, we're just running out of time, but there are a couple people asking Cortex questions. I don't know how familiar you are with the Cortex experiments, but I think some are asking if the output are available. And I guess, and there's also a question about WRF, so a different model, but and I guess the community also, I think in general, is interested in knowing when the WRF, the Cortex CMCC experiments will be coming out. So maybe you can say something on that.
Yeah, so the results I show you is basically from a flagship pilot study of the Codex community. Now the simulation regarding the state, because the project was the flagship pilot project regarding the urban regional climate change was divided in different stage. The stage was a first very stage dedicated to found the cities, and that was selected, and the selected one was Paris. And the first stage regarding short simulation to simulate some extreme events. Now the simulation are finished, and the first common paper and the joint analysis started. And now the next phase for 10 years of simulation at convection permitting scale, so 3 kilometer, will start. And on this regard, I don't know when the data that will be finally available on SGF nodes, for example, but the first joint analysis for common paper errors already started. And regarding the CMCC, I suppose that now the first analysis of but we are talking about a different story. So we are talking about simulation at 12 kilometer first by reanalysis now are starting, and then by CMCC GCM, and the first simulation, the first analysis has started. So I think that I don't know when they will be available on SGF nodes, but I think that the community is moving in sense.
Thank you, Angelo. This has been a very interesting educational webinar. I'd also like to thank the audience, those of you attending now, and those of you who will be watching this at a later date on our CMCC YouTube channel. We hope that you found the webinar valuable, and we look forward to seeing you again in the future. Thank you.
Thank you.